Recording. We're going to start chapter 26, which is our next chapter in the journey through the General Physics 2. Well, you've probably never seen the actual physical textbook or your e-text, right? But I have one of those in my office if you guys want to see it. It's like this thick, it's kind of like maybe like 3 Bibles worth of textbook. So if you're it used to be when I was taking classes, right? We had like physical textbooks. So, so chapter 26 is actually the second chapter that that's gonna be covering midterm number 2, right? So midterm number 2 is gonna cover what we did last week. This week, 27, which is gonna be on current, and 28, which is actually gonna be on circuits. And those of you who are maybe the computer science major may be more interested in this little part of the class where you get to actually get some basic understanding of how a circuit works. Nothing too fancy, just resistors and capacitors and stuff like that. But before we start today, we have another birthday for Stephen Chu. He's actually still alive, unlike the a lot of other people we talk about. In 1997, he got the Nobel Prize in Physics for his research for cooling and trapping atoms using laser. And at that time, well, when I first learned about this, it was really confusing to me because usually when I think laser, I think of hot stuff, right? When the laser hits you, it's actually hot. But he developed this technique that you can actually cool things using laser by just kind of, if you have an atom, right? Got an atom, let's just, with a little cloud around it, right? These guys are always vibrating, right? When they're at room temperature. And what you do is that you use a laser, right? Which is something we're going to learn, has an oscillating electromagnetic field. Let's say this is the electric field. And what you do is you calibrate the electric field so that when the atom tries to go to the right, it's actually trying to fight a uphill potential. So you're just kind of trapping this little atom in this little well here, and it's kind of a cool way to cool things down. And I think he reached 240 millionth of a degree. So he reached in temperature in Kelvin, right? So that's 240 times 10 to the negative 6 Kelvin. Okay, and in case you're wondering, right, room temperature is about 290 Kelvin, right? So he was able to reach that temperature using lasers, which is kind of counterintuitive. And the reason, well, I never actually met him, but he was actually at my commencement ceremony at UC Santa Barbara when I graduated from Santa Barbara in 2000. Yeah, this was right at the end, 2013. He was actually the commencement speakers, because usually at commencement there's a little speaker guy or woman. So this is kind of a cool thing that if you like to play with lasers, right, this is the type of work you could do with lasers. Speaking of lasers, that's the kind of opposite of what he did. I just want to mention, I think those of you who had me last semester, probably I talked about this right before the final, right, where the National Ignition Facilities, which is actually at Livermore, that's only like about an hour from here, they actually was able to achieve fusion with a net energy gain for the first time in the history of humankind last December. So that was kind of a neat thing. But this is kind of like the opposite application of lasers. As opposed to cooling things down with lasers, they shoot like, just imagine like the Death Star, right? All these lasers are just converging on a single point to basically superheat a little grain the size of a grain of rice, in order to get the temperature and pressure high enough so you can actually initiate fusion in that little grain of rice. And it's kind of the opposite application of fusion of lasers, where you heat things up as opposed to cool things down. And it's just surprising that you can do both with the same device, right? Okay, and this is what we're learning about this semester. You may not realize this. Laser, right, is actually, well, it stands for light emissions, but light is actually made of electric and magnetic fields, and we're going to see the connection between the two before we wrap up the semester today. Not today, the semester. But before we get to more electricity and magnetism stuff, we're going to talk about the potential a little bit more, right? And the idea, how does it relate to the electric field, okay, specifically, okay? That way it kind of consolidates what we know, what we learned so far, okay? So it's kind of a neat chapter. I really appreciate that this chapter does this, where, you know, how in chapter 22, we learn about the electric force, right? Two charges, you know, opposite charge attract, like charges repel. We learn how to calculate that. And then in chapter 23, right, we talk about this thing called an electric field. What if you just have one charge, right? It still produces this thing called an electric field around it, right? And then in chapter 24, right, we basically learned this thing called Gauss's law, which is actually a technique to calculate electric fields, right, that have like spherical symmetry, plane symmetry, rotational symmetry, you know, these special cases that, you know, I gave you a test problem on yesterday, right? The last problem was on Gauss's law. And then 25, which is what we covered last week, right? We also introduced this idea called potential energy, right? Right? If you have a single charge here, right, in order to bring another charge close to it, you have to fight against the electric field in order to do that. And that requires you to do work, right? When you do work, right, you're storing potential energy in that system, okay? And then now, right, before we ended up last chapter, we also had this thing called potential without the energy, right? This is always confusing to me between the two. So just think about potential as just voltage, right? This is the kind of removing that second charge once again. So this is a really cool diagram where, right, we learn about forces, right? You can calculate forces if you have two different charges or more, right? But then, right, we use that to derive what the electric field is, right? There's a direct relationship between the electric force and the electric field, right? Right, because the electric force, I'm just going to write this down, right? Let's do this for just point charges, right? Right, this is not always the case. For point charges, right, the electric force is this 1 over 4 pi epsilon naught thing, charge 1, charge 2, divided by r squared r hat, right? But then the electric field, right, is the same thing, but without charge 2, right? Yeah, right? So this you can do with a single charge, right? Just a charge creating a field around it, right? This is forces between two things, right? Right? And remember that when you have forces, right, you can store energy, right, by doing work on a system, as I mentioned, right? And that's actually goes to the concept of electric potential energy, right? So the potential energy for two point charges, right? This is all, once again, 1 over 4 pi epsilon naught Q1, Q2, divided by R, and this is a scalar value, right? It doesn't have a direction to it, right? These are vectors, right? Okay. Neat thing is that while we can also link that to the potential or voltage, right, by just removing the second charge, right? Right, you don't need to do an E, right? It's 1 over 4 pi epsilon naught Q1 divided by R, right? You can see how all these equations are pretty similar to each other, right? Sometimes it has a Q2, sometimes R is square, sometimes R is not, right? And this applies for just point charges, right? So there must be a way for us to relate all four of these things kind of in this little box, okay? And we're going to try to go through that in the first half of this chapter, okay? And that's sort of the point of the first half of this chapter. That way you can actually, if you're given the electric field, you can figure out the electric force, and you can figure out the voltage. Once you have the voltage, right, you can actually figure out what the potential energy is, right? So you can run around this box as long as you have just one of the four quantities. Okay, so remember that change in potential energy is the amount of work you store into the system, right? And that means that the amount of work you did into it, right, you did to it, gives you negative of the amount of potential energy, Okay, there's an opposite sign there because, right, it's the external force that is storing energy into it. So if the external force, right, is losing energy, that energy goes into the system, right? So there's an opposite sign there, right? And this is calculated just like work from chapter, I don't know, 7 or 8, right? Way back in first semester, right? In order to figure out what the work is, right, you do this thing called F dot ds, right? It's the amount of force you apply to an object as you move it around, right? The prime example of this is that if I push horizontally on this chair, I'm doing work to it, right? But if I'm pushing straight down, I'm doing no work because it's not moving at all, right? It's the force basically dot producted with little increments of displacement, right? If you have a constant force, you can pull that out of the integral, right? And that means, right, you get F dotted into this integral of ds, but integral of ds is just kind of like the net displacement, right? The macroscopic displacement, okay? And that's where you come up with this kind of way to remember what work is. It's just force times distance, right? Technically, it's force dot producted with distance, right? Only if the displacement is in the same direction as your force, that's when you have force times distance, okay? Similarly, right, so this is something that we already learned, but what if we have the electric field, right, and we want to calculate the voltage instead? So what you do is that instead of electric force, you replace it with electric field, right? Instead of potential energy, you replace it with potential. You notice that these are all parallel kind of equations, right? They're very similar to each other, right? Okay. And so the change in potential as opposed to change in energy, right, is just the electric field dot producted with the displacement vector, right? So once again, if the E field is constant, which is not always the case, right, this integral simplifies because you can bring the E field out of the integral, right, and this just turns into E dot ds, right? Right? And there's going to be an example of this constant version in a little bit. But what I'm going to do is show you guys a more concrete example where the electric field is not constant, okay? Let's say in this little graph here, right, this is the electric field as a function of position, meaning it's increasing as a function of position. A way to draw this is to draw it in the setup. You can even draw this kind of physically, where I have some x-axis here, right? I can even draw a y-axis, although it's not relevant, right? When x is small, the electric field is small. As x gets bigger, the electric field also gets bigger, right? Does that make sense? Right? Right? The bigger your x value, the bigger the electric field vector is, right? Okay? That's what it looks like. So, let's see if we can find, does it actually ask you to do something? Find and graph voltage as a function of x, okay, as opposed to electric field, okay? So what I'm going to do is I'm going to first go through this kind of a less intuitive and just kind of plugging in, doing the plug and chug type of method, right? So I have the electric field equation here that relates to voltage, right? Okay, so I know that change in voltage is going to be the negative of E dot ds, right? From some initial state to some final state, okay? What we're going to do is that, well, we're going to set V equal to 0 at x equal to 0. So this is where we set V equal to 0, okay, along that x equal to 0 plane. That means the initial voltage, right, is going to be 0, and we're going to move this little charge out to some final voltage where it's some function of x. We don't know where it is yet, but it's going to be some function that we should be able to write in terms of x somehow. Okay? Right? So remember change in voltage is always going to be V final minus V initial. Right? This is already set to 0. So therefore, V final, right, it's going to be some function of x. It's going to be this crazy integral that we have to compute. Okay? Initial, final. Right? Looking at this graph here, right? The electric field is increasing with x, right? So we actually have to figure out what the slope is, right? So the slope happens to be, if we just do some dotted lines here, right? If x is equal to 1, you're actually at 1,000 volts, okay? So the slope is actually 1,000, right? Okay. So let's finish writing in black. So 1,000 times x, that's the slope. And this is going to be in the x hat, I hat direction. So therefore, right, if I write ds, right, once again, I'm going to do dx I hat plus dy j hat plus dz k hat. You don't have to do this yourself when you're, on a time crunch, right? But note that, I hat dot I hat is the only one that's not 0, right? Right? When you dot I hat with j hat, they're perpendicular, right? So therefore, it's actually 0. I hat dot k hat is also 0, right? So these terms doesn't contribute. This is the only one that does. And therefore, initial to final, 100. So x dx, right? The integral of x is just x squared, right? So 100 x squared. Evaluate it from x equal to 0 to x equal to some x position, right? So therefore, the voltage is actually negative 1,000 x squared. Okay? You're right. I did my integral wrong. Right? Over 2, over 2, negative 500 x squared. Good catch. Okay? Okay? So the plot of voltage as a function of x is actually an upside down parabola, right? So a function that's x squared is a parabola, right? And that's what it's going to look like this, okay? Okay. Does that make sense? This is just doing some calculations, kind of plug and chug. You have the equation for voltage to convert electric field into voltage, right? And you're just kind of doing the math, okay? Any questions about this? All right. I'm going to do one more example. Well, I'm going to talk through one more example, okay? So instead of a voltage that's, electric field that's increasing with x, right? If you put two parallel plates that are charged next to each other, right? What happened is that, remember from chapter 23, you get a constant electric field between these guys, right, instead, right? So the nice thing about integrating a constant, right, instead of doing this 100 times x situation, right, if you have a constant, right, the integral, right, let's do this, right, if the electric field is constant, initial to final, so some constant times dx, right, the constant can come out. You just have negative of that constant times, delta integral of dx. Let's just go through all the calculus stuff here, right? Right, integral of dx is just delta x, right? This is the case where you have a similar case as if we have a constant force, right, over some distance, and then you just get whatever that electric field is times, let's just make that a constant electric field. So I go back up, if I can erase this part too. Okay, I'm going to call it E constant. Some constant electric field, whatever that is, okay, times delta x, right? Okay, because right, between two parallel plates, right, you get a constant electric field. Okay? So this is the case where the voltage is just negative of the electric field between the two plates times the distance between them, or the gap size. Okay? So just be really careful about this. Okay? And the distance between them, right, delta x is actually s, so that's why you come up with this equation that delta x is actually, I think it's negative s, right? Okay. Okay. So I'm going to try to turn this, yeah, question?
Can you go back to the previous problem?
The previous?
For that one, since we have that's the voltage, right? Or,
You have, for this one, we have an increasing electric field. So when we plug it into here, we cannot just bring it outside integral. So we actually have to do that integration. And this is where Matthew actually caught my 1/2 problem, right?
but this would be from voltage, right?
This is to calculate the voltage, yeah. To convert.
You said there's like the square can get the electric field as well from this. You said there.
Right. Well, you were given the electric field,
Okay.
right? You want to calculate the voltage. If you're given the voltage, you can also calculate the electric field, right? So it's kind of nice. So as long as I have one of the four corners, right, I can go around this entire box, right? So the two examples, we have the electric field, we have to calculate what the voltage is. Okay? Good question. All right. So let's do a little quick thought, stop to think, which is kind of nice for this book to have this stuff, right? Let's say on the left-hand side here, we have electric field as a, that's drawn on here. So I'll let you interpret what that means, okay? And it points upward, okay? I want to figure out what the voltage is as a function of y, okay? Is it A, right, B, C, D, or this crazy thing, E? Okay? If we have some sort of electric field I'll let you guys interpret what that looks like. Okay? What does it look like if we're trying to figure out the voltage as a function of y, right? Y is horizontal in this case. How many of you guys think it's A? How many of you guys need more time to think? Most of you? Okay. So I'm going to scroll up to the previous example where we also, well, first of all, what is the electric field? Is it increasing as y, or decreasing as y, or constant as a function of y? It's constant, right? So that's nice, right? When we have a constant as a function of y, right, the integral, it gets come out nicely, right, because, right, E dot ds, right, this, if E is constant, we can bring that out. We just have E dot delta S, okay, right? So how would that look like? Is it going to look like a linear function in y? How many of you guys think it's A? 1. How many of you guys think it's constant, some constant voltage? Right, got 4. How many think it's decreasing in the y? Decreasing in the y, okay? What about D? 1. Alex, you think it's D? Okay. It's not going to be E, okay? Don't worry about that. Okay. It's not going to be something funky like this. Okay? So, right? So in this case, right, the electric field is positive, right? It points in the j hat direction, right? So the only part we have to deal with is delta y in the j hat direction, right? Because those are actually dot product to 1, right? So the change in voltage, right, is going to be E times delta y, right? So the further you are in y, the more negative it is. Therefore, it should be which of these graphs now? Is C. Great. Right. Okay. Okay. So just be really careful about, first of all, I think a lot of you guys might have thought A because it's increasing, right? But there is this negative sign in front of the equation, right? Okay. Okay, so that's sort of like the key formula in this section where if you have the electric field, you can calculate the voltage out of it. What about the other way? Okay. So what if you have the voltage and you want to calculate the electric field out of it? Okay. So one of the simple example is that if you have a constant electric field, right? Remember, just like what we just talked about, right? When you have a constant electric field, it's just whatever that electric field in some s direction, right, times delta s, right? In this case, if you have a constant, you can just do some algebra, right? Because if I know what the voltage is, I know what delta S is, I can calculate what ES is. ES is just going to be negative delta V over delta S, right? Okay, anyone can predict what I'm going to do next? I'm sorry? Right, I'm going to turn this into a derivative, right? So what I'm going to do is I'm going to take the limit as delta V over delta S goes to 0, right? When I take that limit, right, that's going to turn it into a derivative, okay? Right? Right? It turns it into a derivative. Right? Which hopefully makes sense, right? To go from electric field to voltage, right? We did an integral, right? To go from a voltage to an electric field, we should do a derivative, right? Because they're anti-functions of each other, okay? So let's do a quick example with a point charge, okay? So we know what the answer is, right? I know what the electric field of a point charge is, right? It's going to be 1 over 4 pi epsilon naught q divided by r squared, r hat squared, right? This is actually not a 1. This should be q, okay? Right? So hopefully we get that answer, okay? So if I want the electric field, right, this is a function of r. So that's going to be an electric field in the r direction. What I'm going to do is I'm going to put a negative sign, do the derivative with respect to r, right? Whatever the voltage function is, q divided by r, right? Okay. If I do this derivative of basically 1 over r, right? Another way to write this always seems to me the easier to write ways to write exponents. Instead of 1 over r, I'm just going to think about it as r to the negative 1, right? Okay, when you do the derivative, the negative 1 falls out in front, right? And then you lower the power by 1, right? So this is actually r to the negative 2 instead. Okay, so these two guys actually cancel each other out. So you just get q over 4 pi epsilon naught, and this is 1 over r squared, right? And since this is the electric field in the r direction, if I were to write the full vector, right, I just have to put this and put it in the r direction, okay? Right, and that's exactly what we calculated from chapter 23, right? Same thing. So nice. Okay, so if you have the voltage, you can calculate the electric field by just taking derivatives. But just make sure you have this negative sign. It's always, there's a negative sign between the two, okay? All right. So let's do one that's a little bit more complicated. Okay. This will involve the chain rule. Okay. Right. So let's say we're given the potential, the voltage for a charge ring. So remember, this is an example from chapter 23 also. We have some ring that has a bunch of charge on it. Okay. And go out in the z direction. Right. At some point on the z-axis, right, we were able to figure out what the electric field is, right? We were also able to figure out, but in this case, they just gave you the voltage as a function of z here, right? And that's what that tells you, okay? And let's see if we can get the same answer we had in chapter 23, right? So, right, to calculate the electric field, right? This is going to be in the z direction, right? The voltage is a function of z, right? I'm not going to, if I take a derivative in the x direction, what happens? What should I do? What should I do with a z if I'm taking derivative in the x direction? Treat it as a what? A constant, right? So if I take a derivative of a constant, what do I get? You get 0, right? So therefore, technically EX and EY also exist, but then those are all zeros, right? So you don't have to calculate them, right? That's why I'm jumping straight into the EZ, okay? Negative, take the derivative, 1 over 4 pi epsilon naught, this complicated stuff with a bunch of square roots. Do you guys know how to take derivative with stuff like buried inside a square root? Do you guys remember how to do that? What's the key word for that? Usually that's for integration. You could technically do a U substitution in here, but there's a thing called the chain rule. Do you guys know? Remember that from first semester? Okay, so the derivative of this, oops, I'm going to bring out the 1 over 4 pi epsilon naught. It's the derivative of whatever this function is, okay, which is, I'm just going to rewrite the function one more time, okay, because I really don't like the, I really prefer to see the function this way. Does that make sense, what I just did? Right, because the square root is in the denominator, so it's -1, but it's a square root, so it's 1/2 power. Okay, so I'm going to take a derivative of this. Then I have to multiply that derivative by whatever the derivative is inside there. Right, that's called a chain rule. Okay. Okay. Derivative of this is you get a -1/2 falling out. Okay, and then you reduce the power by 1, so it gets 3/2, right? And then I have to take the derivative of, multiply that by the derivative of whatever is inside here, right? Okay. And that turns out to be, this is a lot of writing, r squared -3/2, right? Derivative of the stuff inside, right? Well, the r is constant, so that goes to 0, right? This is just 2z, right? Okay. All right, these two cancel each other out. The minus sign cancel each other out. Okay, so I'll just have q over 4 pi epsilon naught. You have a z on top, and then you have a 3/2 power with a negative sign, so that goes in the denominator, right? So z squared plus r squared to the 3/2 power, right? That's going to be the electric field in the z direction, okay? If I want to change this into a vector, I just put a k hat there, right? Okay. Right. Let's check our results from the previous chapter. Oops, it's all the way down the bottom here. All right, let's zoom out a little bit. So does that look similar, right? Or should be the same, right? So all of that integration crap that we did, right, in order to calculate this, right? If you have the voltage, you can just take a derivative and find it. All right? So nice. Okay. This is actually why, right, most of the time we deal with, as opposed to figuring out what the electric force is between some system, if you know the voltage, that's all you need. And voltage is actually always the easiest thing to measure in a lab also. I think you guys were going to do this lab this week, but then I think that was the delay or something like that. So you guys are going to be able to measure voltage on a piece of paper and actually be able to figure out what the electric field is from that. Okay, so measuring voltage is always the easiest thing to do, and that's why you always start with the voltage, and then you just take derivatives, and if you multiply by the charge, then you get the energy. If you want the force, you can go through the electric field and multiply by the charge, and that gets you all around that box, right? We just saw in the beginning. Okay, so Let's talk a little bit more about things that may be a little bit more complicated, right? Where as opposed to just having like a function that's, oh, you're just given some function of the potential or voltage, right? Let's say we're given some drawing, right? Where, maybe in a lab, you're actually able to measure voltage at different points. And let's say, right, on this green line here is some equal potential, meaning on this point, right, you're measuring 10 volts, 10 volts, 10 volts, 10 volts, 10 volts, right? But then on the other line here, let's say it's minus 10 volts, right? Minus 10, minus 10, minus 10, minus 10, minus 10, minus 10. Have you guys used the multimeter yet in the lab? Okay, you're going to get that. Hopefully, it'll be nice if you guys did that yesterday. But, right, yeah, it's a multimeter is the thing that measures voltage, okay? That's sort of the idea of it, okay? The cool thing about it is that if I was to, if I'm some charged particle, right? Imagine you're some charged particle, right? If I'm just moving along this line, right? I'm not going up or down in potential, okay? Okay? But if I wanted to go from the negative minus 10 volts to positive 10 volts, I kind of have to go uphill against the potential, okay? A way to, the analogy of this, so that's why I save space on the right-hand side. So if you were hiking, I'm going to draw a terrible drawing, right? You have some hiking path, and this is usually my favorite one, right? Right? And you're just walking at the same elevation, right? Right? You're walking along the same potential, right? So you don't have to, you're not going to increase or decrease your gravitational potential in order to do that. But if you want to go to the top of the mountain, maybe up here, right? You have to go uphill, right? This is where you have to change your potential. Blue. Blue. No. Right? This is where you change the potential. Okay? So this is like V minus. Let's say that's minus 10. Right? This is like V plus or positive 10 volts. Okay? 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 And whenever you guys are moving charged things from one potential to the other, right? Just think about it. Oh, high potential is uphill, right? Low potential is downhill, right? Okay. Okay. And then you can have even more complicated paths, right? Where you have 3 different potentials, right? Okay. And what we're going to do is we're going to think about well, if you have 3 different potentials here, is there a way for us to calculate, kind of geometrically figure out what the electric field is at each of these points? Okay. So remember that electric field, right, came from the electric force, right? Okay. Okay. If I was to be, some charged particle here, right? Right? If I'm just sitting there, right? I'm not moving, I'm not stuck to anything. If I'm free to move, right? Am I going to go to the negative potential, V minus, or going to go towards V plus? Okay? Imagine yourself, as like a ball on a hill, right? Are you going to roll uphill or downhill? You're going to roll downhill, right? So that means there's going to be some force, right, that's going to push you downhill from where you are straight towards the negative voltage, right, and away from the positive, right? So that means this electric field has to point towards negative voltage and away from positive voltage, right? Okay, does that make sense? How we figure that out? So if I was at this point, it'll point in this direction, and it's actually quite big, okay? Because imagine yourself, I'm going to go back to my hill up here, right? Right? If you were to go uphill like this, right, it's decently steep, right? But if you were to go uphill like this, it's less steep, right? Steep. Right, this is steeper, right? Okay? So the shorter the distance you're trying to go from positive to negative, that's the steeper part of the hill. where if the distance is increased, right, meaning you're walking on a longer path but it's less steep, right, the hill is actually less steep. Okay, I'm trying to do all these hiking analogy, but maybe it's working, maybe it's not. Okay, okay. Therefore, right, the parts where the voltages are actually physically closest to each other, even though this is plus 10, this is minus 10, right? You have to go change this 20 volts in this distance. But by the time you get here, right, this change in 20 volts is spread over a longer distance, and therefore the electric field is actually smaller there. Okay. So let's do another example. So maybe we'll wrap up with this, where we're trying to figure out. Let's say we're given this, potential map, which is what you guys are going to do next Monday. Well, you're actually going to measure your potential map yourself. Okay. Okay. Right. And the grids are 1 centimeter by 1 centimeters. Okay. They want you to estimate the strength and direction of the electric field at point 1, 2, and 3. Okay. Let's see if we can figure that out. So since this is an estimate, right, all we have to do is just kind of do the drawing, right? We don't actually have to calculate the number. Okay. So notice that this is at 0 volts, this is at 100, this is 50, halfway between the two. Right. First of all, right, which way is the electric field going to be pointing? How should we think about that? If we were a little ball on a hill, right, which way is uphill? Uphill is to a higher potential, right, downward. Right, downhill is to a lower potential, right? So you're on this little hill. Imagine you're on a little slanted hill like this, right? Let's go around like this. Okay. So if you're a little ball, you're going to roll downhill, right? So the electric field is going to point this way. Okay. Right. The distance between these potential lines is one of the shortest because we're going to see some longer ones. So when I draw the electric field, right, it's going to be one of the longer electric fields. Okay. This is the electric field at point 1. Okay. That makes sense? All right. So at point 2, which way is downhill? Which way is the electric field supposed to be? All right. Let's vote. Is it to the right? Or is the ball going to roll down this way? Or is it going to go to the left? To the left, right? So that's the direction, right? But the difference, the distance between the voltages are bigger, so it's a slightly less steep hill, right? So this electric field is going to be smaller, right? In magnitude, it's going to point in this direction, right? Right? Don't think it's just going to point to 0, right? That's just an accident, okay? Right? The closer these green lines are to each other, the bigger the electric field, because you're basically making a steeper and steeper hill. Okay? 3 is the harder one, right? It's not going to be y or x, right? It's going to point in this direction, right? And since this is kind of intermediate to the 2, right? It's going to be something between the 2, right? So therefore, right, E1, the magnitude of it is the biggest one. It's the biggest one. Wait, E2, yeah. And then E3 is the intermediate one, and then E2 is the smallest one, right? Because that's where the lines are most spread out. Okay? Okay. All right? Does it make sense how to figure this out? Right? Imagine high voltage is high up on the hill, low voltage is bottom of the hill. Okay? And if you were a positive charge, what would happen? What happens which way would, if you were a negatively charged ball, what would happen to you instead? You roll up the hill instead, right? Everything's opposite if you were fully made of electrons or something like that. Okay. Okay. So that's that example. Got a couple of minutes. Just want to introduce this last thing. It's interesting that the book tried to do this right now, but let's just talk about it real quick. Okay. It's kind of a neat thing with this uphill, downhill rolling situation, right? Let's say, right, I started at point 1 and I want to get to point 2, right? And this green line is 20 volts, this green line is 30, this green line is 40, right? There are multiple paths I can go to get to that point 2, right? I can follow this 20-volt line, right, which requires me to not go up or downhill, meaning doesn't require any work. But then I can make a climb, right, along this B path up to 30 volts, getting an extra 10 volts. And then I'm going to follow this this contour here, right? And then I'm going to make the climb up to 40 volts along this line, right? Right? So that's sort of a longer path, but the change in voltage is still going to be positive 20 volts, right? Okay. What I can do is that this is the way I actually prefer to hike, right? Where I do all the uphills in the morning, I just go straight up the hill, okay? Get my positive 20 volts, right? By this time, you're already at positive 20 volts. But if I want to get to point 2, right, I just walk along this equal potential line, and I get a nice, easy hike after I get my warm-up, okay? So notice that these two are perfectly the same, are two different paths that get you to the same place, right? And technically, there's infinite ways you can do this, right? You can go up here, you can do all kinds of paths, okay? What's going to be interesting is that, what if, right, I follow the red path up to 2, right, which gives me a positive 20 volts, right? But then I go backward go the opposite direction along the blue path. What will be my potential change if I go from 1 to 2 and then from 2 to 1 along a different path? I'm sorry? You will get negative 20 along the blue path, but you gain positive 20 on the red path, right? So this is let's call this the red path, right? Change in voltage, right, backward along the blue path gives you a negative 20 volts. So the change in potential total is actually 0, right? So hopefully that makes sense, right? If you park your car at, at 1,000 feet, you walk up a hill, you go back to the car is not going to be at 2,000 feet, right? Right? So it's not going to change the potential. Okay? And this brings up this idea of a loop. So this is known as a loop. If we go on the red path and go backward along the blue path, back to the same point, right? That's completing a loop, okay? And therefore, when you complete a loop, and we're going to see this when we talk about this next chapter on circuits, right? When you complete a loop, the change in voltage is always have to be 0, right? Hopefully that's intuitively makes sense, okay? And this is known as Kirchhoff's loop law, after this guy, Gustav Kirchhoff, with these crazy beard and slick hair, okay? And apparently he's born in the year 222224 on Wikipedia. Okay, he's I think he's a time traveler, I'm pretty sure. Okay, other than that, or Wikipedia is wrong. Okay, we'll figure out which one's which. Okay, so that's all we're going to cover today. Tomorrow, I'm going to do a worksheet, but then I'm going to cover maybe 20 minutes worth of materials first, okay? Because we're on a shorter week, so we need to cover a little bit more material during the lecture time.